Welcome to BSc Statistics students. In this lesson we discuss second problem of duality. That is, you see the question here. This is what the question will be given in the examination. Solve the following LPP using duality. So using duality procedure, you have to solve this particular question. So what is the question? Primal LPP, that is a given LPP or primal LPP is maximized Z and subject to the constraint here it is given. So by using duality you have to solve, which means you have to consider this primal. This is a primal LPP. Primal LPP. I'm solving the problem. I'm considering this is a primal linear programming problem. Now I'm writing the dual LPP here. Dual linear programming problem. So you have to solve this dual LPP. So first of all, convert. It's very easy. Convert maximization objective function, hence minimization. Zx, here you consider Zx, I am considering Z omega. This is the variable in x variables are given here, x1, x2. So therefore I am considering omega, which will be here right hand side constants, which will be in the objective function of the dual. That is 3 omega 1 plus 5 omega 2. First one finished, objective function. Now you consider subject to the constraints. Subject to the constraints. The constraints are going to be transport matrix of the coefficient matrix. So first of all, this 2, 8 and 40. Objective function right hand side constant. It becomes the right hand side constants. So therefore, 2 into omega 1 plus 8 into omega 2 less than or equal to constants. Therefore, greater than or equal to 40. That is the first constraint. The second constraint. 3 and 4 with 50, that is 3 omega 1 plus 4 omega 2, it is greater than or equal to 50, and omega 1 omega 2 are greater than or equal to 0. So therefore this is what the dual linear programming problem. So for this you have to solve. You see, actually clearly to speak, if you ask me the question, then solvation of this is very easy rather than this, because greater than or equal to constraint we have to apply big M or two-phase method. So whereas here less than or equal to all constraints, therefore by slack variables this can be solved. That simplex table, simplex method, it can be solved. But whereas here you have to use big M method. But anyhow, it was given as duality. Using duality solve this. Therefore you have to solve this and you have to give the solution of primal. Solve the dual, give the solution of primal. That is what the question duality. Using duality means you have to do that, right? So therefore now I solve dual linear programming problem. That is this particular problem. So it is a problem of minimization. So hence you have to convert in terms of maximization. So minimize Z omega is equal to minus maximum of minus Z, that is Z omega. It is equivalent to be minus maximum of minus Z omega. Minus Z omega is minus 3 omega 1, minus 3 omega 1, minus 5 omega 2. This is what therefore the problem enti, what is the problem? Maximize minus Z omega is equal to minus 3 omega 1, minus 5 omega 2. You have to write in this fashion first. This is very, very important. Now the conversion of, this is the problem we are solving in the by using simplex method, that is either big M or two-phase. Now I am using big M method, for which what you have to consider first, greater than or equal to constraints 2R. Then you have to use the surplus variables to convert into inequations. Therefore to convert into inequations, 2 omega 1 plus 8 omega 2, this is what I am writing, 2 omega 1 plus 8 omega 2 minus omega 3, I am using this is surplus variable, is equal to 40. Second equation we have, so the second equation, in the second equation 3 omega 1 plus 4 omega 2 minus omega 4, this is also a surplus variable, is equivalent to be 50. That is omega 3, I write here, omega 3 greater than or equal to 0, omega 4 greater than or equal to 0 are surplus variables. We can write surplus variables, right? And then we have to introduce, because of the initial basic feasible solution was not at all not obtained. So therefore, to obtain initial basic feasible solution, we have to introduce artificial variables. One here, that is let it be omega 5, another here for the equation omega, second equation omega 6. So that is for greater than or equal to constants, we have to introduce surplus variables and then artificial variables omega 5 and omega 6. They write omega 5 greater than or equal to 0, omega 6 greater than or equal to 0 are artificial variables, right? Artificial variables. So these two are artificial variables, these two are surplus variables. This is what the first consideration of converting into the equations. After converting into inequations into equations and obtaining initial basic feasible solution, then you have to that is obtaining basis initial. So for initial solution, you have to now express the initial basic feasible solution. That is what you have to write. I write directly omega b is equal to y5 y6 omega 5. Omega 5. Of course, y5 y6 are the basis vectors. And omega 5, omega 6 are the values here, b inverse b, the values are 40 and 50, the right hand side constant vector. This is what the initial basic feasible solution. You have to put in the first column of the simplex table. I have formulated simplex table 1. You please refer, simplex table 1 is formulated here. So this is what there we have additional vectors y5, y6. I am formulating additional vectors for which, one more particular point we forgot, that is objective function. Objective function should be modified. So which you have to put the cos here. I write the maximize minus z omega is equal to objective function. It is in which you have to consider omega 1, that is what is the 3 omega 1 plus 5 omega 2 plus 0 into omega 4 for omega 3, first 0 into omega 4. These two are surplus variables, plus minus m into omega 5 minus m into omega 6. This is what the objective function. I write here again, maximize minus z omega is equal to 3 omega 1 plus 5 omega 2 plus 0 into omega 3 plus 0 into omega 4 minus m into omega 5 minus m into omega 6. This is what the new modified objective function for this, in which omega 3, omega 4 are surplus variables. We have introduced the cost 0. Omega 5, omega 6 in big M method we have to introduce minus m is the cost, minus m minus m. So now come here, and the cos here 3 minus 3, not plus 3, minus 3 minus 5. So here it is minus 3 omega 1 minus 5 omega 2. Minus 3 omega 1 minus 5 omega 2. This is what the mistake usually did by the students. This is what the only one mistake. In the consideration of maximize minus z omega, you have to consider minus 3 omega 1 minus 3 omega 2. This is what the function you have to consider. So minus 3 omega 1 minus 3 5 omega 2. So minus 3 minus 5, the cos here 0 0 minus m minus m. Okay, now you construct the simplex table. Quickly I'm considering the simplex table 1. Omega b is 40 and 50, that you have to write in the first column of the simplex table. And then you see here remaining columns y1, y2, y3, y4, y5. That is which you refer the equations of the constants 2, 3, 8, 4, minus 1, 0, 0, minus 1, 1, 0, 0, 1. Clear? This is what the y1 to y6 vectors. Okay, so every vector you consider clearly, and so that it will be calculated the net evaluations and remaining all. Yb, what are the basis vectors? Yb, y10, y5, 0, 1, y6, therefore y5, y6. And of course you can refer omega 5 and omega 6 here, omega 5, omega 6, y5, y6. So therefore you calculate z omega, you write the cost here, y5 cost is minus m, y5, y6 cost is minus m. So now you have to calculate z omega, cb xb minus m into 40 omega b here, xb in the place of that omega b, cb omega b, minus m into 40 minus m into 50, hence it is minus 90 m, minus 90 m. Zj minus Cj, minus 2 into m, minus m into 3, minus 5m, minus 5m, minus of minus plus 3. Now you should come for the second one, y2, 8 into minus m, 4 into minus m, you see cbyj minus cj. 8 into minus m, 4 into minus m, minus 12m, minus 12m, minus of minus plus 5. Okay, and come and calculate here, minus m into minus 1, plus m, plus 0, minus 0, plus m. 0, minus m into minus 1, plus m, minus 0, it is m, plus m. Minus m into 1, minus m, plus 0, minus of minus plus m, 0, it is also 0. So this is what the net evaluations for simplex table 1. Now you see in which there are two negatives, minus 5m, minus 12m. The highest negative, the most negative, not highest, most negative is this one. So therefore minus 12m plus 5, minus 12m. So minus 5, minus 12, the corresponding which minus 12m is the most negative. So I am indicating here arrow mark. The corresponding vector is y2, therefore y2 enters. Therefore y2 enters. That is what. Then next the observe the minimum, observe the YIR values, elements in Y2, 8 and 4, elements in Y2. Both are positive. Then you calculate minimum ratio. I am calculating minimum of omega bi by YIR greater than 0. Omega b 40 by 8. This is by 40 by 8. 40 by 8 and 50 by 4. Both are we have to calculate. 40 by 8, 8 5 the 4, 50 by 4, it is more than 12 point something, 12.5. Okay, so therefore it is the least element. So therefore the minimum ratio is 40 by 8, 5. So corresponding to the element is 8. Minimum ratio is 5, corresponding element is 8. So what is the element here? You identify 8. This is what the 8. You round off here and put the star mark. Corresponding vector, it is y5. You indicate arrow mark. Therefore y5 leaves. Therefore y5 leaves. And the pivotal element is 8 and 8 is pivotal element. These are the columns you have to write. 8 is the pivotal element. You write in detail. 8 is the pivotal element. Y2 enters. Minimum ratio is 5. Therefore y5 leaves and 8 is pivotal element. These are the points you have to write after simplex table 1. Then you see here, you put R1 here, you put R2 here. Then you have to write the row operations, relevant row operations. I tell you row operations here, R2 dash, in the next simplex table, R2 dash. R2 dash is you have to convert pivotal element to unity, that is 4, not 4, 8, I'm sorry, 8, R1 dash. In the next simplex table 2, R1 dash, you have to calculate R1 dash. The pivotal element is 8, therefore divide with 8, R1 dash is R1 by 8, that is 40 by 8, 2 by 8, 8 by 8, minus 1 by 8, 0 by 8, 1 by 8. And y5 is leaving, so therefore we can remove y5. There are two procedures here. In the duality, you can by keeping the y5 also you can get the solution, I discuss later. And by keeping the vector, whichever the vector is going to be removed from the, it's leave from the basis, it leaves from the basis, then it can be removed. That is the procedure I calculated in Big M method. In Big M method, whichever the vector which leaves from the basis, then we can remove. That is the reason why y5 leaves and it removes. It can be removed. It can be removed from the basis. It can be removed from the simplex table. So therefore I am cancelling y5. So I am not calculating the calculations for y5. So therefore that is first operation. Second operation R2 dash. R2 dash is nothing but plus R2 and minus 4 into R1 dash plus R2. That is what the two row operations. I calculate row operations here in simplex table 2. Here you observe here the simplex table 2. In the simplex table 2, this is what simplex table 2. So in the simplex table 2, first of all I write the operations. What are the operations here? R1 dash is R1 by 8. That is the first operation. And the second operation is R2 dash. R2 dash is minus 4 is we have to convert to 0, so hence minus 4 into R1 dash, that is required. R1 dash, that is the element multiplication, and multiplication is going to be done for this particular first entered row, that is R1 dash plus R2. This is the two particular operations you have to calculate for R1 dash and R2 dash. This is what first entered row, R1 dash. So therefore you write R1 dash by dividing 8. So I take the operations here, and so that I just note down the operations here. So in the simplex table 2, the operations here, it is the 5. What are the vectors? What are the changes in y? y5, y6. So here y5 is leaving and y2 is entering. So therefore you write y2 enters. There note down first of all y2 enters, and y6 as it is. y2 cost is, you write the cost here, -3, -5, it is 0. And another vector is y6. y5 removed, therefore y6 is here, and y2 cost is -5, and y6 cost is -m. So you have to consider one more, that is minus z omega. This is minus z omega. In the previous simplex table as well, it is minus z omega. You consider minus z omega, since now we are doing maximizing minus z omega. Minimization problem here, so therefore maximizing minus z omega. So therefore now if you calculate r1 dash and r2 dash, r1 dash is r1 by 8. If you do the calculations, you will get 5, 2 by 8, that is 1 by 4, okay, leave it, and it is 1, it is minus 1 by 8, and it is 0, and it is 0, and the last one is also 0. And if you consider r2 dash minus 4 into r1 dash plus r2, then operations will, the calculations will be 30, and calculate 2, it is 2, and it's 0, it's 1 by 2, and it is minus 1, and it is plus 1. You observe y2 is 1 0, y2 is 1 0, and y6 is 0 0 1. That is what. Now you calculate z values, minus z omega. Minus z omega is minus 5 into 5, minus 25, minus m into 30, minus 30m, minus 25, minus 30m, minus 25. This is what the value here. And secondly, minus 5 into minus 2 by 8, that is minus 10 by 8, minus 2m. You see here, I write the values clearly. M coefficient are minus 2m. Minus 5, 10 by 8, minus of minus plus 3. Minus 10 by 8 plus 3. This is nothing but 8 3 is 24. So hence it is plus 14 by 8. Plus 14 by 8. Whatever it is, leave it. And then come over here, and this is what? Minus 5 into 1 plus 0. Minus of minus plus 5, it is 0. And minus 5 into 1, minus 1 by 8, plus 5 by 8, minus m by 2. The coefficient, you write clearly the coefficients here for y3. So I am writing minus 5 by 8. First of all, I write the coefficient of m. Minus m into 1 by 2, minus m by 2, minus of minus plus 5 by 8, minus 0. So plus 5 by 8. So next one is minus m into, this is 0, minus m into minus 1 plus m, minus 0, it is plus m. And next one, 0, minus m, minus of minus plus m, 0. So this is what the calculations, the net value calculations of the net evaluations for the this particular coefficients. Now you see here minus 2m, this is minus m by 2. So 2 negatives here. So therefore m coefficient is highest here, minus 2. Here minus 1 by 2. Therefore this is the most negative. Most negative is minus 2m plus 14 by 8. Therefore put an arrow mark here. The corresponding vector y1 enters. Therefore you note down y1 enters. Therefore y1 enters. And which vector is going to leave the basis? For this you observe the elements here, y1, for y1, 2 by 8, 2. So both are positive. So they calculate minimum ratio. Minimum of xbi, that is omega bi by yar, omega b by y1, that is 5 by 2 by 8. 5 by 2 by 8. And 30 by 2, it is 30 by 2, it is 15. 8 5s are 40, 40 divided by 2, 20. So this is the minimum element, it is 15. It is 20, it is 15. So 15. 15 corresponding to which element? 2. 2 is corresponding which element here? It is 2, this 2. So corresponding to which vector? It is y6. Therefore y6 is also leaving from the basis. y6 is also leaving from the basis. It is an artificial vector. It can be removed from the simplex table. I explained again, you can leave the y6 here. That is one procedure. From that also, I discussed later, from that also you can obtain the solution. No problem. So, but as per my procedure, I am deleting the vector y6. So, because y6 is an artificial vector, it leaves from the basis. You write down here the y6 leaves from the basis. Hence, it can be removed. It can be removed from the entire simplex table. It can be removed from the entire simplex table. And what is the pivotal element? 2. 2 is and 2 is pivotal element. 2 is pivotal element. This is what the calculations you have to do between after simplex table 2. y1 enters, minimum ratio is this, y6 leaves, therefore it can be removed, and 2 is pivotal element. That is what we have to do corresponding to. And then I am formulating simplex table 3. In the simplex table 3, you see, you can observe here, I have considered 4 vectors only, because y6 is also removed. So therefore here you can consider r1 double dash and r2 double dash, which are the 2 particular row operations we have. Now what are the vectors which enters first here? y6 removes, and in the place of y6 y1 enters. Already here y2, and the cos, I write the cos, it is -3, -5, 0, 0. So y2 cost is -5, y1 cost is -3. So right, and what is r1 dash, r1 double dash, r2 double dash, which we have to calculate first. The pivotal element row is r2 dash here, that is 2 here. So therefore 2 is the pivotal element. You have to convert unity, and 2 by 8 you have to convert as 0. So for 2 you have to consider, it is divided by 2. We have to consider it is divided by 2, which means I am writing the operations here, which is in r2 dash. Therefore R2 double dash. R2 double dash is R2 dash divided by 2. The elements divide the same elements itself. You will get the corresponding R2 double dash. Next R1 double dash. Okay, R1 double dash. How do you get R1 double dash? You have to calculate -2 by 8. You have to convert as 0. 2 by 8 corresponding to the element. 2 by 8 it is in R1 dash. Therefore you have to convert as 0, and -2 by 8. We can consider 1 by 4. No problem. So -2 by 8 multiplied by this is what the operation, -2 by 8 multiplied by so which row you have to multiply? R2 double dash, which is entered first, that is R2 double dash plus R1 dash, that is what the row operation required. R1 double dash is -2 by 8, R2 double dash plus R1 dash. So now you calculate the row operations, what you will get the rows. First of all, R2 double dash by simply dividing it, the element 2, what you will get? It is 15. I note the operations here: 15, 1, 0, 1 by 4 and -1 by 2. Can you calculate the second one? That is R1 double dash, the second row. It is -2 by 8 into R2 double dash plus R1 dash, or -1 by 4 into R2 double dash plus R1 dash. So by doing this operation, what you will get? The elements here: 5 by 4, 0, 1, -3 by 16 and 1 by 8. These are the values we can obtain from the row operations. Right, now you have to what you have to calculate? Z omega first, CB into omega B, that is -5 into 5 by 4, -25 by 4. Okay, -25 by 4, 25 by 4 plus not plus minus 15 threes, -3 into 15, 45, 45 into 4, 160 and 4 5 so 20, 180, 180 plus 25, 205, -205 divided by 4. This is value here. Okay, right? And then -5 into 0, -3 into 1, -3 minus of minus plus 3, 0. And then -3, -5 into 1, -5, 0, minus of minus plus 5, 0. Net evaluations for basis vectors y2, y1 must be 0. And then come over here, calculate -5 into -3 by 16, -5 into -3 plus 15, 15 by 16, 15 by 16, -3 into 1 by 4, -3 by 4, okay, -0, okay, leave it, -0, 16, take LCM, so 15 minus 4 4s, 4 3 is 12, 12 minus 15 minus 12, 3 by 16, 3 by 16. Next one, you calculate the next one, the last one, minus 5 into 1 by 8, minus 5 by 8, minus 5 by 8, minus 3 into minus 1 by 2, plus 1 by 8, plus 1, plus 3 by 2, minus 5 by 8, 8 LCM. So minus 5 plus 2 4s, 4 3s, 12, 12 minus 5, 7 by 8. This is what the calculation net evaluations for ZJ minus CJ in the last simplex table 3. Because why I specified last simplex table, you see all the net evaluations are greater than or equal to 0. If all the net evaluations are greater than or equal to 0, then we have obtained the solution. But what you have to calculate, it is a solution of minus Z omega. This is minus Z omega. This is maximize minus Z omega. So we have to calculate minimize Z omega first, and then I will tell you the solution. So minimize Z omega. Therefore, we have obtained maximize minus Z omega is equal to minus 205 by 4, and what you have to write, therefore minimize Z omega is equal to minus of maximum minus Z omega is equal to, this is what the minus maximum of minus Z omega, this one, it is nothing but minus 205 by 4, therefore is equal to plus 205 by 4. What is that? Minimize Z omega is equal to 205 by 4. Therefore, now it is equivalent to be maximize ZX. Original problem. Original problem is maximize ZX. You please see here. Maximize ZX. You see here maximize ZX is equal to 40x1 plus 50x2. So I write here somewhere 40x1 plus 50x2. Then we substitute values here. Alright. ZX is equal to. Right, this is what the solution. So we have obtained a solution, but what you have to calculate, optimum value obtained. Now you have to calculate the solution. How to read the solution? You go and read the solution now here from the values here, values of the final simplex table. This is what the final simplex table. What you have to do, this is a dual solution. Now primal solution is required. What is the dual solution? I am not writing dual solution. This is omega 1, this is omega 2. Omega 1 is equal to 15, omega 2 is equal to 5 by 4. I write here dual solution. The dual solution is dual solution, primal solution. Dual solution is minimize Z omega is equal to 205 by 4 at omega 1 is equal to omega 2 is equal to. What is omega 1? Omega 1 is 15. This is what? The 15. Omega 1 is 15, omega 2 is 5 by 4. Omega 1 is 15, omega 2 is 5 by 4. This is what the values we have obtained. Now we have to obtain primal solution. We got maximize ZX is equal to 205 by 4 at x1 is equal to x2 is equal to. This is what the solution required. Now you see how to read the solution from final simplex table. I have explained in the last problem that how many original variables are there? Omega 1, omega 2, that is y1, y2. Leave the net evaluations for two variables, two vectors, y1, y2, for two vectors, and then start reading the solution in the optimal condition, that is net evaluations. In the net evaluations, what are the original variables of the dual? Omega 1, omega 2, that is for y1 and y2. Leave these two particular net evaluations and then start reading the solution of the primal solution of the primal in the net evaluations of the after the original variables, the net evaluations of the original variables. Start reading the solution of the after these two particular values. Start reading the solution of the net evaluations, which gives the omega 1 x1 x2, which gives the solution of the primal, that is x1 here, x2 here, that is x1 is 3 by 16, x2 is 7 by 8. So therefore x1 is 3 by 16, x2 is 7 by 8. You substitute here, you will get, if you have any doubt, you please substitute 40 into x1, that is 3 by 16 plus 5 into 7 by 8, which will be 205 by 4. Okay, this is what the solution of the primal linear programming problem, that is given LPP, maximize Zx is equal to 205 by 4, at x1 is equal to 3 by 16, x2 is equal to 7 by 8. You write one thing by using fundamental theorem of duality. By using fundamental theorem of duality. Fundamental theorem of duality, you have to write all these things. By using fundamental theorem of duality, minimize Z omega is equal to maximize Zx. That is the first thing. And then omega 1, omega 2, x1, x2, primal solution, dual solution. This is what the solution it is required to give to the original linear programming problem given LPP. Hope you understand. This is what the solution of the primal given LPP by using duality. Thank you.